Okay, I'm not going to go over the exam. If you have questions about it, come and see me. In particular, if you didn't do well on this exam, you should come to the tutorial session. It's on Tuesday evenings, right? Got the time, it's on the web page. But come to the tutorial session and then go through the exam with Lynn. So she'll be happy to do that. Or stop by my office if you have any questions about it. By and large, I think everyone did pretty okay. But certainly there are concepts on that exam with regard to convolution and signal transformations that you will continue to see throughout this semester. So you struggled on that exam. You need to put some additional time into this material now so that you can do better on subsequent exams. So it's not too late. Again, I would encourage you to come and work through the exam with Len during the tutorial session. So last time we talked about inverse Laplace transforms via partial fraction expansion. And today, other than like half a page of lecture here, we're going to spend the rest of the lecture working through different examples. But first, I want to talk about the system transfer function, specifically how what we call a transfer function relates to the impulse response. So, this is the notation we've been using. X of t is our input, y of t is our output, and y of t can be calculated by convolving the input with the impulse response. Well, there are two problems with that. First problem is convolution is hard. Second problem is that we really haven't had a way to get the impulse response. There is a technique, using the differential equation, solving the differential equation, but kind of trying to avoid that. So I'll show you a technique today, one to actually avoid convolution, and then the other technique is a way to get the impulse response from the transfer function. We can get the transfer function from circuit analysis, and we'll work through an example of that as well. Now, in the Laplace transform domain, one of our Laplace transform properties is that convolution transforms as multiplication. So, where h of s is the Laplace transform of h of t, and x of s is the Laplace transform of x of t. H of s, which is the Laplace transform of h of t, is the system transfer function, often just called the transfer function. It contains all the information that's actually in the differential equation description of the system. Has everything about the structure of the system, the relationship between the input and output, except the initial conditions that might be present. So we're going to look at a couple of example problems. So you can use this to solve for the output. The technique that we're going to use to solve for the output is actually multiply the two transforms the Laplace transform of the impulse response, the Laplace transform of the input, multiply those, and then take the inverse Laplace transform of that product using partial fraction expansion. Sounds like a lot of work, but it's almost always easier than convolution and evaluating that convolution. So in this particular example, and right now I'm giving you the transfer function, or it's given in this problem. We'll see a little later on today, you've already done this actually back in circuits 2. We'll see how we can get the transfer function using circuit analysis. But we're given this transfer function and we want to find the response to a unit step. Actually, we're only going to do part A. I think he's got 3 or 4 different inputs to the same system. So H of S is given. It's 18S plus 10 over S squared plus 6S plus 5. Unfortunately, I'm going to go ahead and factor that denominator just in preparation for the partial fraction expansion. And that factors, it has 2 distinct real roots. Quadratics will either, the second order polynomials will either give us 2 distinct real roots, a repeated real root, or a complex conjugate pair of real roots, complex conjugate pair of roots. X1 of t is u of t. So what's the corresponding x1 of s? What's the Laplace transform of u of t? Yeah, it's 1 over s. So instead of convolving, we just multiply these 2 functions. 18s plus 10, s plus 1, s plus 5. Just multiply x1 of s times h of s to get that. Now, unfortunately, with the distinct real roots, it's pretty easy to get the this is the way I usually do it. Write out the 3 terms that we're going to have, and the distinct real roots. You use the cover-up method, the residue method, to determine the coefficient over s. I just cover up s and let s be 0. So I'm going to have 10 in the numerator and then 5 in the denominator. So this would be 2 over s. Sorry, my s's and my 5s look a lot alike. Any question about that? Find the s plus 1 term, coefficient over the s plus 1. Now, don't make the mistake of plugging in s equals 1. You have to plug in, what value of s makes this 0? That's s equal minus 1. So in the numerator, we're going to have negative 18 plus 10, or negative 8. And normally I don't do these in my head. Okay, I would write this out. I would say A1, A2. I would say A2 is minus 18 plus 10 over minus 1 times 4, right? So minus 8 over a minus 4, or 2, if I did that right. Okay. And then that's a plus 2, so a plus sign. And then similarly for the last coefficient with s equal to -5, that's a little bit harder. What is that, -90? -90 plus 10 over, we're covering up s plus 5, so I've got -5 times here, I'm going to get a -4. These numbers are actually pretty nice. I'm going to get -80 divided by +20. Is that right? Negative? No?
Yes.
Yes, no? -80 divided by +20, so -4. So I can write that as a -4. And now the only thing is left is to take the inverse transform. Find y of t. All of these are going to have a u of t. I could factor out the 2, but I'll leave it. I'm going to factor out the u of t. This is 2u of t. The other two are exponential terms, e to the -t -4, e to the -5t u of t. As the answer. Let's see if we can get that same answer using convolution. So to get convolution, I need the impulse response. I've got h of s is 18s plus 10 over s plus 1 times s plus 5. Again, I'm going to have to do a partial fraction expansion on this to get the inverse Laplace transform. S equal -1, I'm going to get -8 over 4 minus 2. And here I get -80 over -4. Is that right? -80 over -4. That's equal -5. We said that was -80 over -4. So 20. Does that look right? So h of t would be -2 e to the -t u of t plus 20 e to the -5t u of t. Now this is the impulse response. It's not the answer. We know x of t is u of t. So now we pull out our convolution table. What's u of t convolved with -2 in -t u of t? Use the convolution table instead of. So this is pair 2. I'm going to get, I've got the -2 I'm going to pull out, and then I'm going to have, actually I'm going to be dividing my -1, so I'm going to write this as 1 minus e to the -t u of t for that term. And then here I'll have plus 20, and then I'm going to be dividing by -5. So I'm going to write 1 minus e to the -5t divided by 5. Again, u of t. So we're going to have a -2 u of t. Let me get rid of this, so that's 4. -2 u of t plus 4 u of t, which is 2 u of t. -2 times a -1 is plus 2 e to the -t u of t. And then the other term, I already pulled up the 4 u of t, -4 e to the -5t u of t. And then here's where we look over there and cross our fingers, and it looks like we got the same result. Right? 2 plus 2 plus 2 minus 4, and then exponential terms of minus 1 and minus 5. So just to prove to you that this does give you the same result as convolution, typically, that wasn't bad. All of those were in the table. Typically, this process is going to get a lot easier. And then more than that, as you start working with circuits, it's relatively easy to get the transfer function from circuit analysis. We can get then the Laplace transform from that if we want it. Let's look at another problem. So we'll see that there are actually kind of multiple equivalent ways to completely describe the input-output relationship for any system. One is the differential equation. Another is actually, we kind of already worked with the frequency response, right? Going right from the differential equation to the frequency response. You can go back and forth. So they're equivalent. Now we've got this transfer function, which we'll see that that's equivalent actually to the differential equation as well. The impulse response completely describes the system. If we know the poles and zeros of the transfer function, we can get the transfer function. So the poles and zeros also completely describe the system. And there's one more way. If we know the input and output for any input, we can actually get the transfer function, the impulse response, the differential equation, all of that. So this is an example of that type of problem. They give us the output when the input's a unit step. So it's not an impulse. So this is not the impulse response. This is the step response. We actually did have a way to get the impulse response from the step response. If you recall, taking the derivative of this would give us the h of t. But let's assume we don't know that. Could we get the transfer function using Laplace transforms? How would we do that? Y of s is h of s times x of s, right? Don't forget that. That's our fundamental relationship. So h of s is the ratio of y of s to x of s. That's true for any x of s. Whatever input I feed that, I'll get some y of s, but that ratio will always give me h of s. So let's use that approach. Actually, I'll give you guys a few minutes. Find y of s, find x of s, and then find the transfer function. I'll give you a few minutes to work on that. So this problem, let's see, I did have a couple of, I have extra copies of these tables. These are just extended versions of tables that are in your book that are a little more convenient to work with. Okay. So for this problem, .27, x of s is 1 over s, and y of s, this is in the table. What do I do with it? It's pair 7. They're pretty close to pair 7. So I've got a 10 in front. There's a 2 here in the numerator, and then it's over s plus 3 cubed. Is that the right one? Does that look right? So h of s. Now, for some other input, I'm going to get, of course, a different output, right? But it doesn't matter. The ratio will always be the same. Will always be the same h of s. So h of s, it's the output over the input. I don't know, find some way to memorize that, because the common mistake is to say it's the input over the output or something. It's a mistake I see a lot, but you find the output by multiplying h by x. The input times the transfer function gives you the output. So the transfer function is the output over the input. So in this case, it's going to be, flip that and multiply, I'm going to have 20s over s plus 3 cubed. Now, the partial, so this is part A, find the system transfer function. That was easy. To find the impulse response, we're going to have to do a partial fraction expansion on this, their Fourier transform pair. This is, kind of a nastier one because it's a repeated root. So it would be s plus 3 cubed plus a2 over s plus 3 squared plus a3 over s plus 3 in general. and you can get A1 relatively easy by the cover-up method, then I'd use the polynomial method to find A2 and A3. Use any method that you want to find those. I'm going to go ahead and give that to you, though, because we're going to look at some other problems. Turns out that this one's 0. Yes.
For YMS, would there be a difference between that's supposed to do?
If I did what?
You pulled out the 10 and like 2 on top, or you pulled out 20 and like 1 on top. Or does it just either matter as well?
Oh, you mean if I put the 20 up front and then just did the partial expansion on that?
Well, I meant like up above when YMS is 10 and 2 over.
Well, the 2 was in the was for my table. So it was pair 7. You know, without this 10, t squared e to the minus 3t transfers as 2 over s plus 3 cubed. And then that 10 is this 10. So I just, is that okay? Okay. So the b term turns out to be 0. And so this becomes minus 60 over s plus 3 cubed plus 20 over s plus 3 squared. And then the h of t is minus 30 t squared e to the minus 3t from this term, u of t, plus 20t e to the minus 3t u of t. Okay. I could verify this result actually by convolving this with u of t to verify that I actually get that y of t. The other thing I could do to verify this result is this is a particular input. It's the unit step, so it's related to the impulse. The impulse is the derivative of the unit step. So h of t should be the derivative of this thing. Okay. So that one doesn't look too hard to differentiate. So but I have to use the product rule. Taking the product of the first term of t squared, I'm going to get 20t e to the minus 3t u of t. And then I'm going to get, taking the derivative of the e to the minus 3t, I'm going to get minus 3 times 10 minus 30 t squared e to the minus 3t u of t. That actually matches at this point, but I'm not really done. 10 t squared e to the minus 3t, and then the derivative of u of t is delta t. Okay, and this was one I think that came up on the exam a lot. Anytime you've got delta t and it's multiplying, if something is multiplying delta t, you want to use the product rule. You evaluate what's multiplying the impulse at the location of the impulse. This impulse is located at t equals 0. If I evaluate this at t equals 0, because of the t squared term, that's 0. That's not always the case. You know, if this t squared weren't there, e to the 0 is 1, this would reduce to 10 delta t, but it wouldn't go away. But because of the 10 squared here, this is 0. It's 0 delta t, or 0. And so it matches. So in this case, it's actually easier to find the derivative of the step response. But now if this had been some other input other than a unit step, I would have had to use this approach to take a ratio. We'll look at one more example. Now, so we'll look at problem 330 here. I'm going to draw the circuit. And here, our input, we've got an input voltage and an output voltage. Those are our output, our given input and output. Now, we could be interested in output current, in which case our transfer function would be the ratio of an output current to an input, in this case voltage, or we might have an input current. Okay. So it depends on the problem, what the transfer function is. Here we're interested in the voltage across this resistor. I'm going to go ahead and put in those values. This is a 1 ohm resistor. This is a 2 ohm resistor. And then these are 1 microfarad and 2 microfarad caps. That's going to make it. But the first thing I do is actually transfer it into the S domain. And in the next chapter, it's on applications of the Laplace transform. We'll see where this comes from. I'm not going to go through it now. You've already seen it in circuits 2, actually back in circuits 1, I think, where you replace this in the S domain, you replace these by the corresponding S domain impedances, 1 over SC. Unfortunately, that's going to be kind of nasty. That's going to be a million 10 to the 6 over 2s, right? 1 over a micro is a million, is the impedance there. And similarly, this is going to be 10 to the 6 over s would be the impedance of that capacitor. Now to find the transfer function, you can analyze this, letting V1 be just V1 algebraically, V1 and then, I don't know, use nodal analysis, leaving V1 as a variable and solve for V0 in terms of V1. The ratio would be the transfer function. It's a little easier often to let V1 be some voltage, and it can be any voltage. It's convenient, actually, just to often let it be 1 volt or 1. If it's a current, let it be 1 amp. Then the output is going to be equal to H of S, right? Because VO over 1, that ratio is just VO. Often it's even easier on these ladder type problems where the circuit is laid out in the shape of a ladder here. The other type of problems you usually work with were these window pane type problems, where you had components like this and a source over here. This technique won't work on that, but a technique that works on these ladder type problems, which usually results in fewer equations in finding the transfer function, is let the output voltage be a convenient value, and then work backwards to find the input. And it's the ratio that's important. And the ratio will be the same for, whatever. We can set the input to find the output, or set the output and work backwards and find the input. So what I usually like to do is set the output here. I'm going to set it to 2 volts. The reason is it's across a 2 ohm resistor. That would give me a 1 amp current there. You could set it to 10, you could set it to 1. Just trying to avoid fractions as much as possible. It's going to get nasty enough. So let So what I'm going to do is work backwards to find out what input voltage would give me 2 volts at the output in the S domain. It is an open circuit voltage, so there is no current flowing there. But I know that this current is going to be 1 amp. So this current would be 1 amp. I'm going to call that voltage Vx, or that node X, relative to, here's my reference potential there at the bottom. I could call this VAB or something, but I'm just going to throw a reference point in there. Now, Vx is pretty simply just this impedance times that current, 10 to the 6 over 2s, plus my output voltage, 2. Okay, that's KVL, taking this loop. Voltage from here to here, I'm going to take that path because I know all the currents, and from Ohm's law I know all the voltages. So usually you want to try and combine these as a rational polynomial, so I can write this as 4 over 2s. Is that right? No. 4s over 2s. 10 to the 6 over 2s, and then plus 4s over 2s will give you the 2. I'm almost done. The next steps I want to do are actually, I know the voltage across this cap, so I can get that current. And then now I can get the total current there. It's going to be the sum of those two. And then I can get the input voltage from that loop. So it's a little bit of algebra. I think it turns out to be easier than working it from a forward method, though. It usually does on these ladder type problems. Now, I said you can let these voltages be anything. You can't let them be 0, right? Because then the input voltage would be 0, and that ratio doesn't exist. But any non-zero value that's convenient. Okay, so let's call this Ix. Ix would be Vx divided by the impedance of that cap. It's going to be S over 10 to the 6, so my S's actually cancel out. Do that right? I think so. It's not too bad. So it's 10 to the 6 plus 4s over 2 times 10 to the 6. This is that current. Now I can get this current, I'll call it IT. IT is Ix plus 1. I'm going to write 1 as 2 over 2 times 10 to the 6 over 2 times 10 to the 6. And then so when I add that, I'm going to get 3 times 10 to the 6 plus 4s over 2 times 10 to the 6. And then we're almost there. Then V1 is going to be IT times 1 plus Vx. So it's going to be 3 times 10 to the 6 plus 4s over 2 times 10 to the 6. That's this current times, that's a conveniently a 1 ohm resistor. So that would give me the voltage. You know, with the current direction, this is the polarity of that voltage, so that's plus minus. Again, the same's here. Well, actually, I don't need to take Ix times that impedance because that voltage is Vx. So plus 10 to the 6 plus 4s over 2s. Now I'm going to put them over a common denominator so I can add them, and then I'll be essentially done. So multiply numerator and denominator here by s. I get 3 times 10 to the 6 s plus 4s squared over 2 times 10 to the 6 s. Then multiply this numerator and denominator by 10 to the 6 and 10 to the 12 plus 4 times 10 to the 6 s and 2 times 10 to the 6 s. So now I've got a 4s squared term, and then I've got plus a 7 times 10 to the 6th s, and then I've got a constant term 10 to the 12th all over 2 times 10 to the 6th s. Okay. Assuming I haven't made any mistakes, not done, that's actually the input voltage when the output is 2, or said another way, if I had this input voltage, whatever this is, that would produce an output voltage of 2. The transfer function is the output over the input, so it's 2 divided by this. So I just flip that over and multiply. I'm going to have multiply by 2, 4 times 10 to the 6 times s, over 4s squared plus 7 times 10 to the 6 s plus 10 to the 12. That is h of s. Oh, I missed the b part. Took us a while to get h of s. We could actually use one of the frequency. It might be a little easier to actually use to get rid of all these 10 to the 6s. Because we've got one of the scaling properties we've used for the transform. I'm not sure that's going to help make it a little nicer, give us smaller numbers to work with, and then we would have to go back to. So W of S is substituting S over 10 to the 6 for S. I'm going to get 4S. Oh, that makes that term nasty though, doesn't it? So it doesn't really help. That's the transfer function. We need to factor this, so have real poles, complex poles. But it's a second order polynomial in the denominator, so we need to factor that out, do the partial fraction expansion to get the h of t. It's just going to be some really funny numbers because of the using microfarads here. Be more realistic, it's probably easier to work this actually as a scaled problem instead of using the microfarads and then scale the result. We can do that as well. Any questions? I think I may have given 31 as a homework assignment. Any questions on this? Okay, that's it for today. We'll look at invertible systems and then stability on Wednesday. That's good.